And now in this lecture we find out the radius of the small circle. In the drawing we have triangle ABC. Triangle ABC is a right triangle. This angle equals to 90 degrees in its size. Angle ABC equals to 90 degrees. Therefore triangle ABC is a right triangle. In addition, we know that side AB equals to 6 units in its length, side BC equals to 8 units. Inside the right triangle ABC we have this small circle and this big semicircle, and our mission is to find out the radius of this small circle. So, first of all, we will implement the Pythagoras theorem on this right triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the big right triangle ABC is AC, and therefore the square of the hypotenuse is AC squared, and AC squared must be equal to AB squared plus BC squared. Here by PT is the operation for Pythagoras theorem. Again, according to the Pythagoras theorem, in this right triangle ABC, AC squared equals to AB squared plus BC squared. Repeat again, in the right triangle ABC, according to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. AC is the missing side, so we leave it as it is. AC squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus BC squared. BC is 8, therefore BC squared is 8 squared, that is 64. So in total, we found out that AC squared equals to 36 plus 64. 36 plus 64 is 100, so AC squared equals to 100. We take out of this equation and finally get that the missing hypotenuse AC is equals to the square root of 100, that is 10. And the length of the hypotenuse AC is 10 units. So right now, AC equals to 10 units in its length. In the next step, we will define the relevant points to this question with letters. We will define the center of this small circle. This point is point P. We will define the center of this big semicircle. This point is point Q. Likewise, we define the point of tendency of tangent AB with this small circle. This point is point N. We will define the point of tendency of tangent AC with this small circle. This point is point K. We will define the point of tendency of tangent AC with this big semicircle. This point is point H. And finally, we define the tangent point of this small circle with this big semicircle. This point is point L. So here you can actually implement rule 2. According to rule 2, the lengths of two tangents from a common start point to a circle are equal. So we have, this is the common start point, point P. From this common start point, point P, we have two tangents to this circle, tangent PA and then tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Well, in our drawing, if we focus on this common start point, point A, from this common start point, point A, we have two tangents to this big semicircle, tangent AB and tangent AH, and according to rule 2, they are equal to each other. That is to say, AB equals to AH according to rule 2. But it is given us the question that AB equals to 6 units in its length, so we can write here that AB equals to 6, and for this equation 6 equals to AB equals to AH, we will derive that AH equals to 6 units in its length. And the length of this line segment AH is equals to 6 units in its length, so I write it down. AH is equals to 6 units in its length. What is the length of line segment HC? Line segment HC is equals to AC minus AH. Again, AC minus AH equals to HC. So HC equals to AC, that is 10, minus AH, that is 6. 10 minus 6 is 4. So the length of line segment HC is equals to 4 units. In the next step, we join points Q and H together by a straight line. Point Q is the center of this big semicircle. Point H is a point on the big semicircle itself. Therefore, QH is the radius of this big semicircle. We define the radius of this big semicircle as B, and therefore QH equals to B. This is the radius of the big semicircle. Here we can implement rule 1. We'll click quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and this is tangent AB, that is a tangent to this circle at point M. We have the radius OM, the radius OM equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. Again, tangent AB will be perpendicular to the radius MO. We can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius QH that is drawn to point H, that is the point of tendency of tangent AC with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Okay, by doing this construction, actually created here, the right triangle QHC. This is the right triangle QHC, and this is angle C that belongs to the right triangle QHC. But angle C, this angle C does not belong only to the right triangle QHC, but angle C belongs also to the big right triangle ABC. So angle C is a common angle that belongs to both triangles, to triangle ABC and to triangle QHC. So we define the size of this angle C as alpha. So in the right triangle QHC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we will focus on the right triangle ABC, the right big triangle ABC. In the right big triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha, according to the same rule that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we will prove that the big right triangle ABC is similar to this small right triangle HQC. So I write it down. Prove that the big right triangle ABC is similar to the small right triangle HQC. So why the big right triangle ABC is similar to this small right triangle HQC. First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABC in the big right triangle ABC, and this angle, and it is equal to this angle, that is actually angle QHC. This one right triangle HCQ. So repeat again, I should know that angle ABC, the big right triangle ABC, equals to angle QHC in the small right triangle HCQ. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is the common angle, it belongs to both triangles, so you can write down that angle alpha equals to itself is a common angle that belongs to both triangles. So if we relate to angle alpha as it belongs to the big right triangle ABC, it will be defined as angle ACB. And it equals to itself. So if we relate to this angle alpha as it belongs to the small right triangle HCQ, it will be defined as angle HCQ. Repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So this is the angle BAC. in the right big triangle ABC, and it is equal to this angle, that is actually angle HQC, in the small right triangle HCQ. Repeat again. We found out that angle BAC in the big right triangle ABC equals to angle HQC in the small right triangle HCQ. They are both equal to 90 degrees from southward, therefore they are equal to each other. So actually proved that all the figures in this big right triangle ABC are correspondingly equal to all the figures in this right triangle HQC. Therefore, the two right triangles are similar to each other according to angle similarity rules. So what we know, we actually found out that the big right triangle ABC is similar. This is the sign of similar to the small right triangle HCQ according to angle similarity rule. And from the fact that the big right triangle ABC is similar to the small right triangle HQC, we will derive that the following relationship exists between their sides. We derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. Okay, again, we will derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. AB is 6. Over HQ. HQ is B, it is the radius of this big semicircle that is equals to V according to our definition, and it is equals to BC is 8 over HC, that is 4. So we found out that 6 over B equals to 8 over 4. 8 over 4 is 2. So 6 over B equals to 2. Here we will multiply this equation by B, and finally we get that 6 equals to 2B. Here we will divide this equation by 2, and finally we get that the missing radius B is equals to 6 over 2, that is 3. So we actually found out that the radius of this big semicircle B equals to 3 units in its length. Likewise, the center of this big semicircle is here at point Q, and point B is a point on the big circle itself. Therefore QB is also the radius of this big semicircle, and therefore QB equals to 3 units in its length. So I write it down. The length of line segment QB is equals to 3 units. It is also the radius of this big semicircle. In the next step, we will join points P and N together by a straight line. Point P is the center of this small circle. Point N is the point on the small circle itself. Therefore, Pn is the radius of this small circle. We will define the radius of this small circle as A. Therefore, Pn equals to A. A is the radius that we are looking for in this question. Here we can implement rule 1 because we have the radius Pn that is equals to A. The radius Pn is on to point N, that is the point of tendency of tangent AB with this small circle. Whenever you have a radius that is on to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points P and K together by a straight line. PK is of course the radius of this small circle that is equals to A according to our definition. Again, we have the radius PK that is on to point K, that is the point of tendency of tangent AC with this small circle. And whenever you have a radius that is on to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. The new rule is rule 15. Okay, click on rule 15. According to rule 15, from an external point of a circle, you draw two tangents to that circle. This is the common external point, point P. From this common external point, point P, we draw two tangents to this circle, tangent PA and tangent PB. By drawing the two tangents PA and PB, we get this angle. This is angle APB that was created by drawing tangent PA and PB to this circle. Then the angle that will be created between the two tangents, repeat again, that the angle that was created by drawing tangent PA and tangent PB to this circle is angle APB. This is angle APB, and according to rule 15, it's angle bisector, so the angle bisector of this angle APB must pass for the center of the circle. So the angle bisector of this angle APB must pass through point O, that is the center of this circle. So again, whenever you draw two tangents from a common standpoint, point P to the circle, you will create between the two tangents PA and PB, this angle will be created. Angle APB will be created. And according to this rule 15, the angle bisector of this angle APB must pass from point O, that is the center of this circle. So we can actually implement rule 15 in our drawing. Why? Because in our drawing, we will focus on this common external point, point A. From this common external point, point A, we have two tangents to this circle, tangent to the small circle, tangent AN and tangent AK. For drawing the two tangents AN and AK, we get the angle A. Again, this angle A is created by drawing tangent AN and tangent AK to this small circle. And according to rule 15, the angle bisector of this angle A must pass through point P, that is the center of this small circle. Again, the angle bisector of this angle A that was created by drawing tangent AN and AK to this small circle, the angle bisector of this angle A must pass through point P, that is the center of this small circle. So if we found out that the angle bisector of this angle A must pass through point P, that is the center of this small circle. So I write it down. The angle bisector of angle A passes through point P. Repeat again, the angle bisector of this angle A passes through point P, that is the center of this small circle. We will continue to focus on this common example point A. On this common example point A, we have two tangents to this big semicircle. We have tangent AB and tangent AH. By drawing the two tangents AB and AH to this big semicircle, we created the same angle A. Again, the same angle A was created by drawing tangent AB and tangent AH to this big semicircle. Now we can implement rule 15. According to rule 15, the angle bisector of the same angle A must pass through point Q, that is the center of this big semicircle. Again, the angle bisector of this angle A that was created by drawing tangent AB and tangent AH to this big semicircle, the angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. So I will draw the angle bisector. So first of all, this is the angle bisector AP that must pass through point P, and the angle bisector AQ must also pass. The angle bisector angle Q must pass from point Q, that is the center of this big semicircle. So I write it down. If I found out that the angle bisector of the same angle A passes also through point Q. You can see here that the angle bisector of this angle A passes through point P, that is the center of this small circle, and the angle bisector of the same angle A passes also through point Q, that is the center of this big semicircle. So if we define of this, if we define the side of this angle A is 2 theta, then the angle bisector PA bisect angle A into 2 halves. Each half must be equal to theta, of course. Likewise, we have the angle bisector AQ that bisect the same angle theta into two halves. Each half equals to theta. This is angle theta, and this is the second half, this is also angle theta. So the angle bisector of this angle A passes through point P and also for point Q, and it is obvious that the angle bisector of this angle A must pass also for point A. Again, the angle bisector of this angle A must also pass for point A. So write it down. The angle bisector of the same angle A passes also for point A. In conclusion, we shall find out that the angle bisector of this angle A passes through points A, P, and Q. So I write it down. We shall find out that the angle bisector of this angle A the angle bisector of angle A passes for points A, P, and Q. And again, the angle bisector of this angle A passes for points A, P, and Q. But the angle bisector of any angle is a straight line. Again, the angle bisector of any angle is a straight line. And especially the angle bisector of this angle A is also a straight line. So I write it down. The angle bisector of angle A is a straight line, and the 3 points A, P, and Q, they pass through the straight line that is the angle bisector of angle A. Or we can write down actually in conclusion that all the 3 points A, P, and Q, they are located on the same straight line. Okay, all the 3 points that are A, P, and Q are located on the same straight line. And the straight line is the straight line of angle, is the angle bisector of angle A. The straight line that all the 3 points A, P, and Q are located is the angle bisector of angle A, that is a straight line. So we can find out that all the 3 points A, P, and Q are located on the same straight line. Or in other words, we can write down that line segment APQ is one straight line. Again, line segment APQ is one straight line. Okay, so line segment APQ is one straight line. And for the fact that line segment APQ is one straight line, it means that this angle theta is a common angle that belongs to both triangles. Angle theta belongs to the small right triangle A and P, and angle theta also belongs to the big right triangle, triangle ABQ. So I write it down. In conclusion, I should found out that angle theta is a common angle that belongs to both triangles, it belongs to the small right triangle A and P, and this angle theta also belongs to the big right triangle, triangle ABQ. Repeat again, angle theta belongs to the small right triangle AP, and this angle theta also belongs to the big right triangle, triangle ABQ. In the next step, we will focus on this right big triangle, triangle ABQ. On the right big triangle, triangle ABQ, this angle equals to theta, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, we will focus on this small right triangle, triangle A and P. In the small right triangle A and P, this angle equals to theta, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus theta. According to the sum rule, that the sum of the angles in any triangle is equals to 180 degrees. In the next step, we will prove that the big right triangle ABQ is similar to this small right triangle, triangle NP. So right now, we will prove that the big right triangle ABQ this big right triangle ABQ is similar to this small right triangle, triangle ANP. So, why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually, this is angle ABQ. In the big right triangle ABQ, and this goes to this angle, that is actually angle ANP. In the small right triangle APN. Repeat again. Actually found out that angle ABQ in the big right triangle ABQ equals to angle ANP in the small right triangle APN. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, it is a common angle that belongs to both triangles. So you can write down that angle theta equals to itself. It's a common angle that belongs to both triangles. So if we relate to this angle theta as it is belongs to the big right triangle ABQ, it will be defined as angle BAQ. And it equals to itself. So if we relate to this angle theta as it is belongs to the small right triangle NAP, it will be defined as angle NAP. Repeat again. This equation means that angle theta equals to itself. We just call two angle theta two different lengths. Angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually this is angle BQA. In the big right triangle ABQ, and it is equal to this angle, that is actually angle APN, in the small right triangle ANP. Repeat again. Actually found out that angle BQA in the big right triangle ABQ equals to angle APN in the small right triangle APN. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually found out that all the figures in this big right triangle ABQ are correspondingly equal to all the figures of this right triangle ANP. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. I actually found out that the big right triangle ABQ is similar. This is the sign of similar to the small right triangle APN according to angle similarity rule. And for the fact that the big right triangle ABQ is similar to the small right triangle ANP, we will derive that the following relationship exists between their sides. We will derive that side AB of the big right triangle ABQ over side AN of this small right triangle ANP equals to side BQ of the big right triangle ABQ over side ANP of the small right triangle ANP. Repeating again, we will derive that side AB of the big right triangle ABQ over side AN of the small right triangle APN equals to side BQ of the big right triangle ABQ over side NP of the small right triangle ANP. AB equals to 6 over AN. AN is the missing side, so we leave it as it is. And it is equals to BQ. BQ equals to 3. It is the radius of this big semicircle that is equals to 3 units in its length. over NP. NP equals to A. It is the radius of this small circle. That is the radius that we are looking for in this question. So we should find out that 6 over AN equals to 3 over A. Here we cross multiply this equation and we get that 6 times AN equals, we get that 6 times A equals to 3 times AN. Here we divide this equation by 3. And finally we get that the missing side AN is equals to 6A over 3 is 2A. So AN equals to 2A units in its length. This is the missing side AN, and it is equals to 2A units in its length. So I write it down. AN equals to 2A units. We know that AB equals to 6 units, according to what is given as a question. We just right now found out that AN equals to 2A, therefore the missing line segment NB must be equal to AB minus AN. Again, NB equals to AB minus AN. So NB equals to AB, that is 6, minus AN, that is 2A. So in total, NB equals to 6 minus 2A. So I write it down. We should find out that this line segment NB is equals to 6 minus 2A units in its length. In the next step, we will do a construction, that is to say, from this point P, from this point P, that is the center of this small circle, we will draw perpendicular on BQ. Again, from point P, we will draw perpendicular on BQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, we can derive quadrilateral NPBN. Inside this quadrilateral NPBN, by doing this construction, we can derive quadrilateral NPBZ. So inside quadrilateral NPBZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral NPBZ, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at its left angle if not a square. So we relate to this quadrilateral NPBZ as a right angle because it has 4 right angles. So write it down, this quadrilateral NPBZ is a rectangle. But we also know that the opposite sides of the rectangle are equal to each other. So in rectangle NPBZ, side NP must be equal to the opposite side BZ. But NP equals to 8 is the radius of this small circle, that is the radius that we are looking for in this question. So NP equals to 8, therefore BZ must be also equal to A. Likewise, according to the symbol in the same rectangle NPBZ, side NB must be equal to the opposite side PZ. But NB equals to 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. What is the length of this missing line segment ZQ? From the law, it is very easy to see that ZQ equals to BQ minus BZ. Again, ZQ equals to BQ minus BZ. So ZQ equals to BQ, that is 3, minus BZ, that is 8. So in total, ZQ equals to 3 minus 8. is the length of line segment PQ. Actually, we find out the length of this line segment PQ by implementing Rule 10 in our drawing. Okay, so repeat quickly. Actually, in the drawing, we have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally, this point L. And whenever you have an external notch between two circles, you can implement Rule 10. So I'll click quickly on Rule 10. According to Rule 10, if two circles touch each other externally, here we have the drawing two circles, and they touch each other. Again, if two circles touch each other externally, in the drawing we have two circles and they touch each other externally at this point P. So if two circles touch each other externally, then the straight line that connects their centers together, the straight line that connects their centers together, we have here the center of this small circle is at point M. The center of this big circle is here at point O, and the straight line that connects the centers together is of course the straight line MO. This straight line MO must pass through point P, that is the through point P, that is the touching point of those two circles. Again, the straight line MO must pass through point P, that is their touching point. Or MPO is one straight line. Again, MPO is one straight line according to this Rule 10. We can actually implement Rule 10 in our drawing. Why? Because in our drawing we have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally at point L. The center of this small circle is at point P. The center of this big semicircle is at point Q. And the straight line that connects the centers together is of course the straight line PQ. And according to this rule, to Rule 10, the straight line PQ must pass through point L, that is their touching point. Again, the straight line PQ must pass through point L, that is their touching point. Or PLQ is one straight line. Again, PLQ is one straight line. If PLQ is a straight line, then PQ is also a straight line. But what is the length of PQ? PQ must be equal to PL plus LQ. So I write it down. PQ will be equal to PL plus LQ. And only because of the fact that PLQ is one straight line, PQ will be equal to PL plus LQ. So PQ equals to PL. PL is the radius of this small circle, that is the radius that we are looking for, and it is equals to A plus LQ. LQ is the radius of this big semicircle, that is equals to 3. So in total, we actually found out that PQ equals to A plus 3. In the next step, I'll copy this right green triangle PZQ in a new page, and we will implement the Pythagoras theorem on this right green triangle PZQ. Here by PT is the evolution for Pythagoras theorem. Side PZ equals to 6 minus 2A. Side ZQ equals to 3 minus A. And the length of the hypotenuse PQ is A plus 3. of 3 plus a. So actually, this is the green right triangle PZQ that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle PZQ, PQ square equals to PZ square plus ZQ square. Again, PQ square equals to PZ square plus ZQ square. So I write it now. PQ square, that is the square of the hypotenuse, equals to PZ square plus ZQ square. The hypotenuse PQ equals to 3 plus a units in its length, therefore PQ square is 3 plus a square, and it is equals to PZ square. PZ is 6 minus 2a, therefore PZ square is 6 minus 2a square plus ZQ square. ZQ is 3 minus a, therefore ZQ square is 3 minus a square. Actually, found out that 3 plus a square equals to 6 minus 2a square plus 3 minus a square. We will open the brackets on both sides of this equation, and we will get that 3 plus a square equals to 3 squared, that is 9, plus a square plus 2 times 3 times a is plus 6a. And it is equal to, on the other side of the equation, we have 6 minus 2a squared. 6 minus 2a squared equals to 6 squared, that is 36, plus 2a squared, that is 4a squared, minus 2 times 6, minus 2 times 6 is minus 12, and minus 12 times 2a is minus 24a, plus 3 minus a square. 3 minus a square equals to 3 squared, that is 9, plus a square, minus 2 times 3 times a is minus 6a. So here we have 9 on both sides of the equation, so 9 we can cancel. And we also have here a square on both sides of the equation, so a square also we can cancel. After cancelling those two expressions, in this side of the equation we left only with 6a. In the other side of the equation we have 36 plus 4a squared, and minus 24a minus 6a is minus 30a. Here we subtract 6a from this equation. After we subtract 6a from the equation, this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 36 plus 4a squared minus 38 minus 6a is minus 36a. In conclusion, we can find out that 36 plus 4a squared minus 36a equals to 0. Here we will divide this equation by 4, and we will get that 4a squared over 4 is a squared, minus 36a over 4 is minus 9a, and finally 36 over 4 is 9. 0 over 4 is 0. In conclusion, we should find out that a squared minus 9a plus 9 equals to 0. So actually this is a quadratic equation. And again, a squared minus 9a plus 9 equals to 0. It is a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation. and x is the variable that we're looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0, the variable that we are looking for is a, so x equals to a. The coefficient a equals to 1, the coefficient b equals to minus 9, and finally the coefficient c equals to 9. The only thing that is left to do is to put the data of our specific quadratic equation inside the general formula for x, and we find out the value of the values of a because x equals to a. We do it now and we get that x equals to a, so a equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81, minus 4 times a. A is 1, so minus 4 times 1 is minus 4, times c. C is 9, so minus 4 times 9 is minus 36. So inside the root we have 81 minus 36 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So if we found out that a, that is the radius that we are looking for, the radius of the small circle a equals to 9 plus minus square root of 81 minus 36 is 45. So inside the root we left only 45 over 2. So here we will have two solutions that are possible for a. The first solution for a, that is the radius of the small circle, a equals to 9 plus square root of 45 over 2. So according to the first solution for a is the radius of the small circle. According to the first solution, the radius of the small circle a equals to 9 plus square root of 45 over 2. But this expression 9 plus square root of 45 over 2 is definitely greater than 3. But the problem is that the radius of this small circle a cannot be greater than 3. Why? Because of the fact that the radius of the big semicircle equals to 3 units, and the big semicircle is definitely bigger than the small circle. The radius of the big semicircle must be greater than the radius of this small circle, or the radius of this small circle must be less than 3, that is the radius of this big semicircle. So if we found out that the radius of this small circle a must be less than 3, but according to the first solution for a, the radius of the small circle a is greater than 3. Therefore, this solution is incorrect solution. We cancel this solution, because the radius of the small circle must be less than 3, but we found out that according to the first solution for a the radius of the small circle is greater than 3. Therefore, this solution is incorrect solution. We cancel this solution and we left only with the second solution that is possible for a. So the second solution for a is the radius of the small circle. The second solution for a is that a equals to 9 minus square root of 45 over 2. So a equals to 9 minus 45 is 9 times 5, so we substitute 45 by 9 times 5 over 2. So A equals to 9 minus the square root of 9 is 3, so inside the root we left only with 5 divided by 2. So according to the second solution for A, the radius A of this small circle equals to 9 minus 3 times square root of 5 over 2 units in its length, or in terms of numbers, this expression 9 minus 3 times square root of 5 over 2 is equals to 1.146 units. And this is the solution to the question. I repeat again, actually found out that the radius A of this small circle is equals to either 9 minus 3 times square root of 5 over 2 units, so in terms of numbers, this is equals to 1.146 units. That is definitely less than 3 units. That is the radius of this big semicircle. So in the next step, I'll summarize the lecture. In this lecture, we found out the radius of this small circle. So in the drawing, we have the right triangle ABC. We know that side AB equals to 6 units in its length, side BC equals to 8 units in its length. Inside the right triangle ABC, we have this small circle and also this big semicircle. And our mission is to find out the radius of this small circle. So first of all, we implemented the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle ABC is AC, therefore the square of the hypotenuse is AC square, and it must be equal to AB square plus BC square. Repeat again, according to the Pythagoras theorem in the right triangle ABC, AC square equals to AB square plus BC square. AC is the missing side, so we leave it as it is. AC square equals to AB square. AB is 6, therefore AB square is 6 square, that is 36, plus BC square. BC is 8, therefore BC square is 8 square, that is 64. So in total, we have found out that AC square equals to 36 plus 64, that is 100. AC square equals to 100. We took out of this equation, finally found out that the AC hypotenuse AC equals to the square root of 100, that is 10. So yeah. AC equals to 10. Here, we defined the relevant points to this question with letters. We define the center of this small circle, this point is point P. We define the center of this big semicircle, this point is point Q. We defined the point of tendency of tangent AC with this small circle, this point is point K. We define the point of tendency of tangent AB with this small circle, this point is point N. We define the point of tendency of tangent AC with this big semicircle, this point is point H. And finally we define the touching point of this small circle with this big semicircle, this point is point L. So here we can implement rule 2. If we focus on this common point point A, we have two tangents to this big semicircle, tangent AB and tangent AH, and according to rule 2, they are equal to each other. AB equals to AH according to rule 2, but AB equals to 6, so we can write it that AB equals to 6, and from this equation 6 equals to AB equals to AH, we will derive that AH equals to 6 units in its length. This line segment AH is equals to 6 units in its length. What is the length of line segment HC? From the drawing it is very easy to see that HC in total equals to AC minus AH. Again, HC equals to AC minus AH. AC is 10, AH is 6, so in total HC equals to 10 minus 6, that is 4. In the next step, we join point Q and H together by straight line. QH is the radius of this big semicircle. We define the radius of this big semicircle as B. We can implement here rule 1 because we have the radius QH, that is 1 to point H, Therefore, according to rule 1, whenever you have radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. By doing this construction, we're going to do the right small triangle QHC. In the right small triangle QHC, we have this angle, that is angle C. But this angle C belongs also to the right big triangle, triangle ABC. So angle C is a common angle that belongs to both triangles, triangle HQC and the big triangle ABC. So we define the size of this angle, the common angle C is alpha. In the right triangle HQC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third dimension angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, if we focus on the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third dimension angle must be equal to 90 degrees minus alpha, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we proved that this right big triangle ABC is similar to this small right triangle HQC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that the angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I should have proved that all the angles of the right big triangle ABC are correspondingly equal to all the angles of the right triangle HQC, therefore those two right triangles are similar to each other according to angle similarity rule. So repeat again, we actually found out that the right big triangle ABC is similar to the right small triangle HCQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC of the big right triangle ABC over side HC of the small right triangle HCQ. Repeat again. We derive that side AB of the big right triangle ABC over side HQ of the small right triangle HCQ equals to side BC of the big right triangle ABC over side HC of the right small triangle HCQ. AB is 6, HQ is B, it is the radius of the big semicircle, BC is 8, and HC is 4. So we have found out that 6 over B equals to 8 over 4. 8 over 4 is 2, so in conclusion we have found out that 6 over B equals to 2. We multiply this equation by B and finally found out that 6 equals to 2B. Here we divided this equation by 2 and finally found out that the missing radius of the big semicircle B equals to 3 units in its length. Yeah, B equals to 3 units in its length. QB is also the radius of this big semicircle that is equals to 3. In the next step, we join points P and N together. At that time, Pn is the radius of this small circle. We define the radius of this small circle as A. A is the radius that we are looking for in this question. We can implement here on 1 because we have the radius Pn is equals to A. The radius Pn is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, PK, we join points P and K together at that time. PK is the radius of this small circle that is equals to A. The radius PK is drawn to point K, that is the point of tendency of tangent AC with this small circle. And whenever you have radius that is drawn to the point of tendency, then tangent PK will be perpendicular to the radius KP. If PK, then tangent AC will be perpendicular to the radius AP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, I presented to you a new rule and we implemented the new rule in our drawing. The new rule is rule 15. According to rule 15, if from an external point of a circle you will draw two tangents to that circle, then the angle that will be created between the two tangents is angle bisector must pass through the center of the circle. So in the drawing here, this is the common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. By drawing the two tangents PA and PB, we created this angle, angle APB. And according to this rule 15, the angle bisector of angle APB must pass through point O, that is the center of this circle. Again, the angle bisector APB must pass through point O, that is the center of this circle. So it is the angle bisector of angle APB that was created by drawing tangent PA and tangent PB to this circle. So whenever you draw from a common standpoint to a circle two tangents, you will create an angle, and the angle bisector of that angle must pass through the center of the circle. Okay, I can implement all 15 in our drawing. In our drawing, if you focus on this common standpoint point A, on this common standpoint point A, we have two tangents to this small circle, tangent AN and tangent AK. By drawing the two tangents AN and AK, we created this angle A. Again, this angle A was created by drawing tangent AN and tangent AK to this small circle. And according to rule 15, the angle bisector of this angle A must pass through point P, that is the center of this small circle. Again, the angle bisector of this angle A must pass through point P, that is the center of this small circle. Repeat again, I should found out that the angle bisector of angle A must pass through point P, that is the center of the small circle. Likewise, we will continue to focus on this common standpoint point A. From this common standpoint point A, we have two tangents to this big semicircle, tangent AB and tangent AH. By drawing the two tangents AB and AH, we can deduce the same angle A. Now we can implement rule 15. According to rule 15, the angle bisector of this angle A must pass also through point Q, that is the center of this big semicircle. Again, the angle bisector of this angle A must also pass through point Q, that is the center of this big semicircle. So we can write down that the angle bisector of the same angle A must pass also through point Q. And it is obvious that the angle bisector of this angle A must pass also through point A. Again, the angle bisector of angle A must pass also through point A. And from that, we found out that the angle bisector of this angle A must pass through points A, P, and Q. Then again, we found out in conclusion that the angle bisector of angle A passes through points A, P, and Q. Okay, the angle bisector of angle A passes through points A, P, and Q. But the angle bisector of any angle is a straight line, and especially the angle bisector of this angle A is a straight line. Okay, the angle bisector of angle A is a straight line. And therefore, we actually found out that all the 3 points A, P, and Q are located on the same straight line. What is the straight line? The straight line is the angle bisector of angle A. Okay, all the 3 points A, P, and Q are located on the same straight line, and the straight line is the angle bisector of angle A. That is the straight line, of course. So all the 3 points A, P, and Q are located on the same straight line. Therefore, APQ is one straight line. Again, APQ is one straight line. Okay, if we found out that APQ is one straight line, no, line segment APQ is one straight line. It is the same. Also, we can, in other words, say that instead of saying that points A, P, and Q are located on the same straight line, we can say that line segment APQ is one straight line. Okay, line segment APQ is one straight line. Okay, line segment APQ is one straight line. Therefore, we can say that if the size of this angle A is 2 theta, then the angle bisector PA bisects angle A into 2 halves. Each half equals 2 theta. Likewise, the angle bisector of the same angle A, but that is QA bisects angle A into 2 halves. Each half equals to theta. So we actually found out that this angle theta is a common angle that belongs to both triangles. Angle theta belongs to the small right triangle A and P, and angle theta also belongs to the big right triangle ABQ. Okay, again, actually found out that angle theta is a common angle that belongs to both triangles. It belongs to the small right triangle A and P, and angle theta also belongs to the big right triangle ABQ. We'll focus on the right triangle ABQ. In the right triangle ABQ, this angle equals to theta, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle ANP, this angle equals to theta, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus theta according to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the big right triangle ABQ is similar to this small right triangle ANP. So write those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, this is a common angle that belongs to both triangles, so we can write down that the angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I shall prove that all the triangles of the right big triangle ABQ are correspondingly equal to all the triangles of the right small triangle ANP. Therefore, those two right triangles are similar to each other according to angle similarity rule. So repeat again. We actually prove that the right triangle ABQ is similar to the small right triangle ANP according to angle similarity rule. Repeat again. The right big triangle ABQ is similar to the right small triangle ANP according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. Repeat again. We will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. AB is 6, AN is the missing side, so we leave it as it is. BQ is the radius of the big semicircle, that is 3. And ANP equals to A is the radius that we are looking for in this question, the radius of the small circle. So we found out that 6 over AN equals to 3 over A. Because multiply this equation and finally found out that 6a equals to 3 times an. Here we divided this equation by 3 and finally found out that the missing sign an equals to 6a over 2 is 6a over 2 is 2a. So the missing sign an equals to 2a units in its length. So an equals to 2a and ab equals to 6, therefore the missing line 7 and b equals to AB that is 6 minus AN that is 2A. So in total, the missing side NB equals to 6 minus 2A. In the next step, from point P, we draw perpendicular on BQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and PQ. This point is point Z. By doing this construction, we get that quadrilateral NP BZ. Inside quadrilateral NP BZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the side of this 4 angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 angle must be equal to 90 degrees in its side. So inside quadrilateral NPBQ, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this a rectangle, if not a square. So we relate to quadrilateral NPBZ as a rectangle because it has 4 right angles. Okay, so quadrilateral NPBZ is a rectangle. But we also know the double sides of a rectangle are equal to each other. So a rectangle NPBZ, side NP must be equal to the opposite side BZ, but NP is 8, therefore BZ must be also equal to 8. Likewise, according to the sum rule, in the same rectangle NP BZ, side NB must be equal to the opposite side PZ, but NB is 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. What is the ref of the missing line 7 ZQ. ZQ equals to BQ that is 3 minus BZ that is A. So in total ZQ equals to 3 minus A. We have an external arch between this small circle and this big semicircle, that is to say they are touching each other externally at point N. And whenever we have an external arch between two circles, you can implement rule 10. I repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together must pass for their touching point. In other words, you have two circles and they touch each other externally at this point P. The center of this small circle is at point M. The center of this big circle is at point O. And the straight line that connects the centers together is the straight line MO, of course. This straight line MO must pass for point P, that is their touching point. Again, the straight line MO must pass for point P, that is their touching point. Or MPO is one straight line. Again, MPO is one straight line. We can actually implement rule 10 in our drawing, because in our drawing we have an external launch between this small circle and this big semicircle, that is to say they are touching each other externally at point M. The center of this small circle is at point P. The center of this big semicircle is at point Q. And the straight line that connects the centers together is the straight line PQ. This straight line PQ, according to rule 10, must pass for point N. Again, the straight line PQ must pass for point N, that is their touching point. Or PLQ is one straight line. Again, PLQ is one straight line. If PLQ is one straight line, PQ is a straight line, and the length of PQ must be equal to PL plus LQ. PL is 8, is the radius that we're looking for, the radius of this small circle, and LQ equals to 3. So in total, PQ equals to A plus 3. In the next step, I copied the right triangle PZQ in a new page and implemented the Pythagoras theorem, this right triangle PZQ. This is the right triangle PZQ that I copied from the original drawing according to the Pythagoras theorem, and this right triangle PZQ, PQ square equals to PZ square plus ZQ square. Again, PQ square equals to PZ square plus ZQ square. PQ is A plus 3, therefore PQ square is A plus 3 square, and it is equals to PZ square. PZ is 6 minus 2A, therefore PZ square is 6 minus 2A square, plus ZQ square. ZQ is 3 minus A, therefore ZQ square is 3 minus A square. So in conclusion, we actually found out that 3 plus A square equals to 6 minus 2A square plus 3 minus A square. We open the brackets on both sides of the equation, and finally found out that 3 plus A square equals to 3 squared, that is 9, plus A square, minus 2 times 3 times 8, that is 6A, equals to 6 minus 2A square. 6 minus 2A square equals to 6 squared, that is 36, plus 2A squared, that is 4A squared, minus 2 times 6, that is minus 12, and minus 12 times 2A is minus 24A, plus 3 minus A squared is 3 squared is 9, plus A squared is minus 2 times 3 times 8, that is minus 6A. Here we have 9 on both sides of the equation, so 9 will get cancelled, and we have also A squared on both sides of the equation, so A squared also will get cancelled. After we cancel those two expressions, in this side of the equation we have to leave with 6A. In the other side of the equation we have 36 plus 4A squared, minus, here we have minus 24A minus 6A is minus 38. Here we subtract 6A from this equation, and finally found out that in this side of the equation we have nothing, that is to say 0. On the other side of the equation we have 36 plus 4A squared, and minus 38 minus 6A minus 36A. So in conclusion, we actually found out that 36 plus 4A squared minus 36A equals to 0. We divided this equation by 4 and finally found out that 4A squared over 4 is A squared, minus 36A over 4 is minus 9A, and 36 over 4 is 9. So in conclusion, we actually found out that A squared minus 9A plus 9 equals to 0. This is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0, the variable that we are looking for is a. So x equals to a, the coefficient a is 1, the coefficient b is minus 9, the coefficient c is 9. The only thing that is left to do is to put the data for our specific quadratic equation inside this general formula, for x, and we find out the value of a, because x equals to a. We did it and found out actually that a equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81. Minus 4 times a is 1, so minus 4 times 1 is minus 4, times c. Minus 4 times c, that is 9, is minus 36. So inside the root we have 81 minus 46 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. In conclusion, we found out that a equals to 9 plus minus 81 minus 36 is 45 divided by 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 9 plus root of 5 over 2. This expression 9 plus root of 45 over 2 is greater than 3. But the radius a of this small circle cannot be greater than 3 because of the fact that the radius of the big semicircle equals to 3. Therefore, the radius of this small circle must be less than 3. So this solution is the correct solution. We cancel this solution and we're left only with the second solution that is possible for a. The second solution for a is that a equals to 9 minus 4 to 45 over 2. 45 is 9 times 5, so we substitute 45 by 9 times 5, and finally found out that a equals to 9 minus square root of 9 times 5 over 2. The square root of 9 is 3, so in conclusion, in total the value of this expression is 3 times square root of 5. Inside the root we left only with 5 divided by 2. So in conclusion, we found out that the radius a of this small circle equals to either 9 minus 3 times square root of 5 over 2 units. So in terms of numbers, the radius of this small circle a equals to 1.146 units. That is less than the radius of this big semicircle, that is 3. Okay, thank you very much.